Hello, my name is Joe Park, and today I'll be presenting on non-proportional hazard survivor analysis using the Cox-Time model. Before we dive in, let's look at the core values of survival analysis. I have divided them into three perspectives. Technically, survival analysis is unique for handling cancer data. This allows us to estimate the time to event, even with incomplete observations, which is the main difference from standard regression. Theoretically, we use Kaplan-Meier curves and the hazard function to define risk. These are the foundation of the Cox framework. Finally, the business value is the ultimate goal. By predicting the time of customer churn, we can manage risks proactively rather than just reacting. Now, let's look at the limitations of previous models. The first limitation of previous models is linearity. Traditional Cox models assume a linear combination of covariates, which fails to capture complex nonlinear relationships in real-world data. To solve this, DeepSurf introduced neural networks to modern non-linearity and improved performance. However, proportional hazard assumption remained a challenge. Even with DeepSurf, the model assumed that risk stays constant over time. This makes it impossible to describe dynamic changes in risk, which we call non-proportionality. Today's Cox time model finally breaks free from proportional hazards assumption. Its mechanism has two main steps. First, it ensures computational efficiency. By using case control sampling, it reduced complexity O(n) squared to O(n), making large-scale deep learning possible. Second, it expands expressiveness. By injecting time t directly as an input, it eliminates the pH assumption and models non-proportional interactions. Let's look at the traditional Cox model. It is the product of a baseline hazard and a linear predictor. One key engineering detail is that we do not include a bias in the linear function gx. Mathematically, the bias is observed into the baseline hazard, which can hurt the model's identifiability. This is why we must remove the bias in our neural network's output year later. To estimate the parameters, we aim to maximize the partial likelihood. In our deep learning framework, this is equivalent to minimizing the negative log likelihood loss. However, a major engineering problem occurs: the global risk set, Ri. To calculate the denominator, we must scan the entire survival group at every event, resulting in O(n) squared complexity. This quadratic growth makes it nearly impossible to scale for large data sets. Ultimately, this creates a direct conflict between the statistical need for global information and the local nature of mini-batch training. To solve the efficiency and training issues, the authors introduced case control sampling. It has two key mechanisms. First is the event indicator, DI, which makes the model focus only on actual events. Second is the weight, WI. Sampling only a small part of the population distorts the density. So this weight corrects that distortion and ensures the sampled likelihood converges to the original value. Next, the authors transform the likelihood into negative log likelihood loss. Here, the magic of derivatives happens. Notice the log WI term. Since it's a constant determined during sampling, it becomes 0 during partial differentiation. This is a brilliant engineering trick. It allows us to include complex statistical corrections for integrity without adding any extra computational burden during backpropagation. The result is a simple, stable loss function that focuses only on the sampled events. The authors propose one-to-one sampling, selecting only one control subject to maximize efficiency. While individual updates might have high variance or noise, the neural network is optimized through tens of thousands of updates. As different control subjects are selected over time, the accumulated results converge to the same direction as using the entire risk set. In short, repeated training filters out the noise. There are 4 core engineering advantages of one-to-one sampling. First, it achieves O1 complexity, which means the computation per event is fixed regardless of the data size. Second, it offers massive scalability, allowing the model to handle big data with constant computing resources. Third, it provides stable gradients because repeated training cancels out the noise and creates a smooth learning flow. Finally, it ensures high efficiency by minimizing computational overhead while outperforming complex existing models. This box plot proves the statistical validity of one-to-one sampling. As data set grows to 10,000, the blue box, n equals to 1 sampling, perfectly converges to 0 error. Surprisingly, its accuracy is just as good as picking 4 or 8 subjects. This is because the high variance from a single sample is effectively smoothed out as the neural network undergoes thousands of stochastic gradient updates. Therefore, we can achieve unbiased estimation with O1 complexity, as the sampling noise is naturally canceled out through repeated learning cycles. Now, we can move forward with confidence. To expand model expressiveness, the authors replaced the linear predictor with an MLP. However, the high degrees of freedom as neural networks can lead to numerical instability when passed through the exponential hazard function. To solve this, they introduced an L1 regularization specifically applied to the network's outputs Gx, T. Unlike typical weight decay, this output L1 penalty keeps the predicted risks near 0, ensuring mathematical robustness while maintaining the high performance of the neural network. The key innovation is loosening the proportional hazard assumption. In traditional models, time terms in the hazard ratio are canceled out, making the risk ranking fixed over time. In contrast, Cox-Time directly injects time t as an input feature. Since time terms are not canceled out, the network can compute nonlinear interactions between time and covariates. This means the model can learn that a specific feature, like contract type, might be dangerous in the first months, but become less important as time goes on. This allows us to model dynamic patterns like crossing survival curves, where risk rankings change over time. To derive the final survival probability, we must integrate the hazard function. However, since the neural network is a black box, direct integration is impossible. To solve this, we use discretization, transforming the integral into Riemann sum. The Breslow estimator acts as the width of rectangles, and the neural network provides the height. By summing these areas, we can accurately approximate the continuous survival curve. The Breslow estimator represents the shared baseline density for the entire dataset. To get the cumulative hazard, we multiply its density by the individual risk and sum it up over time. However, checking every event time during prediction causes a computational bottleneck as the data size and grows. To solve this, the authors used a hybrid approach. The model trains in continuous time, but performs inference on a random time grid. This allows Cox-Time to produce precise survival curves while minimizing computational overhead. Next, we have two key metrics to evaluate our model. Since Cox-Time is dynamic, we need time-dependent metrics. First, CTD measures real-time ranking accuracy. It checks if the model correctly assigns lower survival probabilities to those who actually experienced an event at a specific time. Second, IBS measures calibration accuracy. It calculates the mean squared error between the predicted curve and the actual outcome. A lower IBS means the predicted probability is mathematically closer to reality. To verify the model, I personally selected the IBM Telco customer churn dataset. With 7,000 customers and a high canceling rate of 73%, I identified that survival analysis was essential rather than standard regression. The decisive reason for this choice is the dataset's clear violation of the proportional hazard assumption. In the telecom industry, churn risk is highly non-linear. For instance, risk levels between different contract types frequently cross or fluctuate over time. These time-varying effects make it the perfect benchmark to prove the structure flexibility of Cox-Time implementation. This is the Google Colab environment where I implemented the entire Cox-Time model. To ensure absolute reliability, I built a 4-step pipeline using PyTorch, covering everything from pre-processing to evaluation. First, I processed 7,000 samples using standard Scholar and cast them to float32 for PyTorch optimization. I paid special attention to these data types because numerical precision is critical for preventing training instability in deep survival models. Second, I designed a lightweight 2-layer MLP architecture with 32 nodes. I integrated batch normalization and dropouts to maximize model expressiveness while preventing overfitting, which is common in structured data. Third, I used 5-fold cross-validation with early stopping to ensure optimal generalization. Finally, I converted the predicted risks into survival probabilities to calculate CTD and IBS, verifying the model's superiority on unseen test data. The final results from the five-fold validation are definitive. Cox-Time recorded an overwhelming C-index of 0.9459, and more importantly, it reduced the IBS error rate by 55.5% compared to the baseline. This high performance suggests that the non-proportional hazards I observed earlier were indeed present and successfully captured by the model. As shown in the Breer score graph, while the traditional model's error spikes over time, Cox time stays stable. This allows our model to follow local data patterns flexibly, capturing rapid risk changes that traditional models completely miss. In short, Cox time provides the structural flexibility and efficiency needed for next-generation survival analysis. In conclusion, this study successfully overcame the pH assumption through ON optimization and direct time injection. Quantitatively, we proved a significant leap in predictive performance. However, from an engineering perspective, we acknowledge the computational overhead during inference due to numerical integration. To solve this, future research in PC hazard models for faster inference or time-dependent XAI to explain the black box nature of a model will be key. Combining these techniques will lead to more practical and reliable survival analysis systems. This concludes my presentations. Thank you for listening.